Hello and welcome everybody to the presentation of our paper Analyzing Vectorized Hash Tables Across CPU Architectures. I'm Maximilian and this is joint work with Lawrence, Anna and Tillman. So if you take a look at the research output from the last couple of years, you will find many papers on hash joins, how to parallelize hash joins, also on hash tables and the best hashing schemes and like different scenarios. And you will also find papers on vectorization. And what you will also find if you take a look on how hash maps are used in industry is that industry hash map implementations like Upside's Google hash map or Facebook's Folly F14 hash map, they all use vectorization. However, we find that the trend is that modern processors are more and more heterogeneous. This means like there are many more ARM CPUs becoming more important. IBM is still working on Power, with Power 10 coming up. Everybody's building their own ARM architect or ARM servers, and yeah, of course, Intel and AMD are continuing to improve their x86 processors. So modern processors are becoming more and more heterogeneous, and there are hash tables which use vectorization. And now the question is, how do vectorized hash table designs that are out there perform under these heterogeneous SIMD instruction sets? To understand or to answer this question, we first want to understand how a hash table works in general. So in a very scalar, in a scalar case where you don't use any vectorization, imagine that you have some array of keys, like your data that you want to look up in memory somewhere. It's like a larger chunk of memory. And now you want to search for key 5. And how you would do it in a classic linear probing hash table is you would query a hash function. The hash function will tell you where to start searching for key 5, in this case at index 0. However, at index 0, we find key 9 and not key 5. Hence, we have to linearly probe throughout the hash table. And because we walk step by step, this hashing scheme is called linear probing until we find key 5 or we can reach an exit condition. So that's scalar linear probing. Let's also introduce SIMD, which is basically vectorization. So in regular coding, scalar coding, if you have an array of numbers and you want to increase every number by 1, you would loop over the array and do +1, +1, +1, +1, +1, +1. This took you 5 addition instructions to increase every number by 1. The SIMD way is basically thinking data parallel about this. So instead, you would have a second vector, so to say, containing just ones, and then you would perform vector addition, which can be done within a single instruction in your CPU. So you would only use a single addition instruction and therefore be more efficient. And that's basically SIMD in a nutshell. Now, how can we use SIMD to implement vectorization how can we use SIMD to implement vectorized hashing schemes? So the first approach is what we call vectorized linear probing. And in vectorized linear probing, you really take linear probing and just perform the key comparisons in parallel. So you linearly walk through the array and check if the keys are equal. There are some intricacies like with alignment, and you need to check for validity, for example. But the gist is you assume that you can compare your keys directly in your SIMD register. Of course, this doesn't work for string keys, only works for integer keys, and your degree of parallelism might be limited. For example, if you have 64-bit integers, then this will not reach a high degree of parallelism. Now there is a sort of intermediate step done sometimes, for example, by Upside's Google HashMap. And in this case, we introduce fingerprints. Fingerprints you can imagine as small meaning either 8-byte or 16-byte short hashes that represent the key. And this enables us to have a higher degree of parallelism. So you can see, like here, we can use double the amount of comparisons because we can compare more at once with shorter data types. Also, it enables us to be independent of the key data type. So if your keys were variable length strings, now we can still use vectorization to compare their fingerprints. So this has some advantages. And the last step we could make is optimize the memory layout of this. So this is bucket-based comparison. And because this is like the main hashing scheme, or like we sort of walk through these hashing schemes step by step in the paper. So it's like what we end up with all the optimizations. In bucket-based comparison, we have the fingerprints in a bucket. And the bucket is like a collection of data. And then the hash map itself becomes a collection of buckets. And each bucket is aligned, like cache line aligned for your CPU. And then not only the fingerprints are stored, but also the key value pairs. So you have them cache local. As soon as you access the fingerprints, probably the prefetcher of your CPU was smart and already prefetched the key value pairs you're going to access. Furthermore, each bucket has some metadata attached to it. For example, allowing for early exit conditions if you know your bucket hasn't overflown or has overflown, and so on. So that's the basic level of abstraction in a BBC-based hash map. And now, again, I want to stress that there are many platforms out there with different vector instruction sets. So on x86, you might be familiar with SSE, AVX2, AVX-512, which are different extensions with different vector register lengths on x86. On ARM, there's Neon, which is basically only 128-bit registers, but there's also SVE. And SVE already becomes very interesting because it's a whole new way of programming a vectorized program, because it is vector length agnostic. So basically you compile once and you run on any CPU implementing SVE, and you don't think about the vector register size. And Power has just one type of extension, which is VSX. And the first insight we make in the paper is that it's really important to find common levels of abstraction across these ISAs. So if you just port one level of abstraction, let's say move masks from x86 to ARM or to Power, it might work, right? You can use a sim library that provides implementations for all of this. But the problem is that it might not be the best way to solve the problem you're actually solving on that ISA. There might be an instruction that might be more suitable for the problem at hand. So it's like always important. You have to reconsider again and again and again on the platform you're having to work with, like, what is the best way to solve my problem. And then we went ahead and implemented like a big amount of hash maps with like small algorithmic variations and so on. You can read all about that in the paper. And now we need to evaluate the hash maps. And basically, we always have to consider at least a three-dimensional problem. We have a system, so like which CPU are we using or which server are we using? And as you can see here, we have two x86 servers, Intel and AMD. We have an ARM server and we have a Power server. And then we can fill up the hash table to a certain load factor. So if you can imagine a completely empty hash table, or like just a few slots are filled, if you find something, you will probably end up at the result on the first slot. And the more full it is, like the harder it gets because you have to do this linear probing more. And the successful query rate basically says, okay, how many of the keys I'm requesting in my get operation on the hash table are actually in the hash table. And because like the probability is higher if the key actually exists that we can abort earlier, a lower successful query rate will also be harder to answer. So, and the very important here is that we want to maximize performance while minimizing memory utilization. If you just throw a bunch of DRAM onto the problem, right, then everything becomes perfect hashing. You never, like, your load factor goes down if you increase your hash map size, and you will find everything on the first slot, or you won't find something. And in this case, everything, like, there's nothing better you can do than linear probing. So we always want to say, okay, we want to minimize memory utilization to reduce costs or something, and then we want to maximize performance given that constraint. And the benchmark I want to discuss here in the presentation, and there are many more like benchmarks in the paper, but it's like the main benchmark showing for integer keys and values that vectorized hashing schemes perform better than scalar hashing schemes. And what you see here on the left is the system dimension. So we left out the AMD x86 system here for simplicity. But we have an Intel system, we have an ARM system, we have a Power system. And we are going to consider three classic or scalar hash maps: linear probing, Robin Hood hashing, and chain hashing. We are going to consider vectorized fingerprinting and bucket-based comparison with 8-bit and 16-bit fingerprints. So for insertions, where we fill up the hash table up to a certain load factor and on average count how many operations or million operations per second we can perform, we will find a pattern here that is reoccurring throughout the benchmarks, which is for smaller load factors, because we are like in the area of perfect hashing, right? The scalar hashing schemes will perform quite well and will outperform vectorized hashing. But if you go into the regions of higher load factor, that's the point where the scalar hashing schemes become really bottlenecked, and the vectorized hashing schemes actually outperform them. And we can already see that bucket-based comparison always comes up on top at load factor 90. And considering lookups, we, of course, again, here need to vary the successful query rate in this case. So the load factor is fixed and we vary the successful query rate. And at load factor 50, every second slot is filled. So you will see here for successful query rate 100, still linear probing performs quite well because your probing sequences are short. But if you go down already to like a small successful query rate, your vectorized hash tables outperform like even 2x or more the scalar implementations. You will already also find some microarchitectural details we discuss more in the paper. For example, like here on ARM, you see that 16-bit fingerprints on BBC perform a lot better than 8-bit, while on Power there's basically no difference between the two. Now let's increase the load factor to an even harder setting. And now we see, okay, consistently across all successful query rates, bucket-based comparison outperforms everything else except on Power, where vectorized fingerprinting is a bit better. But in general, like scalar hashing schemes are outperformed by vectorized hashing schemes. And this is, again, the takeaway. So BBC gives good speedups across load factors. So compared to linear probing from 1.4x on average, like depending on the successful query rate, up to like 2.7x on average at load factor 90. And this is why we say in the paper, okay, BBC is like a good general purpose drop-in replacement for your standard hash map in many scenarios. And of course, there are like details for each architecture, for each like there are implementation details, and this is all in the paper. And a second benchmark that is particularly interesting are string keys. So here we consider AMD and Power, and you will find in the red colors bucket-based comparison, in the blue colors linear probing for integer keys and for string keys. And let's start with insertions again. And it's a similar pattern that performance of course gets worse for the scalar schemes over the period of increasing the load factor. And also you find that integer performance, like for a fixed hash table, is better than a bucket-based than string performance, because we don't have to do any string comparison. But what is really interesting, and it's more visible here in the lookup setting, is that for very high successful query rates, the bucket-based comparison performance approaches linear probing string performance, but the lower the successful query rate, the higher the benefit of using vectorization is, because you won't have to do as many string comparisons. You can basically just compare the fingerprints. So the string performance of bucket-based comparison actually approaches the integer performance. And here you get like enormous speed ups compared to linear probing for these settings. And if you go to load factor 90, again, we see that bucket-based comparison outperforms linear probing. You can basically barely see the blue line, which is linear probing with string keys here, while bucket-based comparison is still kind of still very visible and performs quite well. So again, string keys usually, like if you would just templatize your hash table in strings, right? You would use standard string comparison as the default string comparison operator, and this is slow. So this is why vectorized hash tables using fingerprints perform so well here, and give us enormous speed ups up to 6x. And yeah, that is the string key benchmark. To give an overview of the paper again, so I introduced 3 hashing schemes to you: vectorized linear probing, vectorized fingerprinting, and bucket-based comparison. And we focused on the latter in the 2 benchmarks I presented to you. We find that BBC performs well, and there are many other things to consider, like payload size, like your distribution, like multi-threading, and so on. But for all of these settings, BBC generally is a good hashing scheme. And last, I did not show this here in the presentation, but in the paper we provide a rule set for practitioners based on our experimental insights, like let's say a flowchart on which hashing scheme you should use in your particular workload. But again, BBC is a good general choice. And here you can find our code. It's all open source. So thank you so much for your attention. I'm happy to connect. Let me know if you have any questions, and see you around.